Hi, my name is Nicholas Wiley, and today we're going to be deriving expressions for pressure and temperature as functions of altitude. Now, before we get into anything, let's get a picture of what our system is. So what we have this pocket of air that's going to be ascending to some altitude z. Now, um, for this, we need to understand this pocket of air, the altitude is known, the pressure is known, therefore the volume and the temperature are all known. What we want to do is we want to get an expression that shows us the pressure and the temperature at this certain altitude. Okay. Did I say pressure and temperature? I believe I said that. Okay, so for our system, we need to make three crucial assumptions. Number one, we need to understand that this is adiabatic, meaning that no heat is lost or transferred from the system to the surroundings and vice versa. Secondly, what we need to understand is that this is going to be a reversible expansion, meaning that the pressure inside of our pocket is going to be equal to the pressure outside of our pocket, the external pressure. And last but not least, we need to understand that what we're working with is an ideal gas. This is going to make it very possible for us to do this. All right. So now that we got all those assumptions out of the way, we can start moving into these equations, transforming them into what we need them to be. So the first equation that we're going to need is we're going to need the basic equation for static fluids. It's going to be the change in pressure over the change in altitude is going to be equal to the density of our fluid, air, multiplied by G. Now, another assumption I forgot to inform you of was that as we increase in altitude, we are going to call that a positive Z, which means that our value of G, which is downwards, is going to be negative. I'll just slide that in right now. Now, with this, what we know about density is we know that density is going to be equal to mass divided by volume. What do we know about an ideal gas? We know that PV equals nRT. So what we can actually do with that is we can simply just plug that in. So here we are. We just did a little bit of reorganizing real quick. Now, another thing that we can see to realize that'll make our lives a little bit easier is we have mass over moles. Now, what is that going to be? That's going to be big, cursive kind of M. That's going to be our molecular weight of our gas. So what we can do with this is we can simply just plug it in up here. We have to remember to keep in that G as well. So we're going to have mgp, molecular weight, acceleration due to gravity times temperature, times pressure, all over RT. Okay. So this is a very crucial equation for us. I think I'll leave this up here. Yeah, I think we're going to leave this up here. So now that we're at this point, we have a few directions that we could go in. We have our three different things that we're going to be using. All our independent variables, we have all three of those in our equation right now. We have the derivative of pressure, we have the derivative of altitude, and we have temperature right here. Now what we need to do is we need to isolate it so that we only have two independent variables. We have three right now. That would be practically impossible for us to do unless we did a little bit of, I believe it would be solve IVP, either way. So what we're going to want to do is we're going to want to get rid of this temperature. We're going to want to substitute something in for that so that we can really crunch down and get to what the pressure is going to be as a function of Z. So what do we know about the temperature of this system? Well, what we do know is the first law of thermodynamics, and this is going to help us get there. So what is the first law of thermodynamics? We know that the change in internal energy is going to be equal to the change in heat, and that is going to be, we're going to subtract the external pressure multiplied by the change in volume. Okay, so now that we're here, we don't see any temperature involved. But actually underneath the surface, we can see that there is. Since this is an adiabatic system and we have an ideal gas, what we need to know is, first and foremost, this is gone. That's going to equal 0. That was our first assumption. Now our third assumption was this is an ideal gas. Now this change in internal energy is only going to be dependent upon the temperature now. So what we can do is we can make this into a function of temperature. Okay, so how are we going to do that? Simple definition that you may know is that the partial derivative of internal energy over the partial derivative of temperature at a constant volume with the derivative of the temperature as well. What is this going to equal for us? This right here is going to equal the specific heat at a specific volume. So what can we do? We can substitute in, we can rearrange this equation. So I'm just going to fill it in right up here. So our change in internal energy is now going to be equal to this, which is the specific heat with respect to derivative multiplied by, or in accordance with the derivative of temperature. So that is going to be equal to our P external. Now this was the second assumption we made. Look at that, all of our assumptions are coming into play. We know that this is a reversible expansion, meaning that the pressure inside of the system is going to be equal to the pressure outside of the system. Okay, so that becomes P. We'll just move that over. Equals pressure times the derivative of the volume. All right, we're starting to look pretty good. We're getting somewhere. So what can we do with this now? Well, we do, again, know that what P is equal to. P is going to be equal to nRT. So P is equal to nRT over V. So we can just substitute that in. Now, an important thing I would like to say real quick, we are going to be dealing with a specific volume, so the moles no longer matter to us. It helps with this equation up here, but now that we're really getting into it, the moles no longer matter to us because this is a specific volume. So, okay, this looks good. And what we had a dV over here before, I believe. Yes. Okay, now we're looking pretty good. So now that we have two different differential expressions, what we're going to do is we're going to integrate them side by side. So what's this going to become? First, we're going to divide this by t, divide this, well, it's already divided by v. And actually, I guess that's all we really need to do. Okay, so let's make these integrals. I'm going to skip a few steps. I'm just going to go straight into the integrals. So what we know is that this is going to be a constant value. The specific heat at a specific volume. This is a constant known value for us, for our ideal gas. And then we're going to be integrating the derivative of the temperature over the temperature itself. This is going to be equal to R, which I also forgot the negative. I'm sorry about that. We still have that negative from before. This is going to equal negative R, but I said that I was going to put it in. Now I'm actually going to take it right back out. Now, why would I do that? Rather than us just having that negative sign stick there for now, what we're actually going to do is we can simply just flip our bounds of integration, and then we're all set. Okay, so what are our bounds of integration going to be? I told you before that we have a known altitude, which means we have a known pressure, a known temperature, a known volume. So what we can do is we can call our lower bound that at the pocket, at the altitude of the pocket at which we knew. Well, we know the temperature there, so T1 all the way up to T. Then for this, we flip it, V1 over V. Okay, now we're looking pretty good. So now we can integrate this, and this is going to be a simple log. So we have, and also, I'm going to divide by R over here. You'll see why in a second, just to get all the nonsense onto this side. So we have the specific heat at a specific volume over R, multiplied the natural log of T over T1 is going to equal to V1 over V. Now we're getting somewhere. Okay, this is looking pretty good. I believe this is correct. Yes, this is correct. Yes? Yes, this is correct. Okay. I did leave out the ln, sorry, the natural log. Now, what can we do with this? A rule of logs and natural logs, as you may know, or if you didn't know, is that we have this value up here. We can move it up here. Whatever is being multiplied by the log. Okay. Now, what else can we do? We can remove this natural log. raise both sides to the e power, or raise it to the e, however you prefer to say it. Now, what can we do with this? This term is kind of stuck. There's nothing we can really do with it. We can move it over there, but we haven't made any progress. So what we're actually going to do is we're going to take this right here, which we know V1 is going to equal nRT over P. Oh, get rid of the RT over P. But V equals RT, PV. Okay, yes. So what we're going to have is RT1 over P1, all of this divided by RV, RT over P. Okay, I believe I did that right. Yes, I did. All right, so now what we're going to do is we're going to substitute that in here. So we see that we have this constant r in the numerator of our numerator, and we have this r in the numerator of our denominator. So these are simply just going to cancel out. Okay. Now what are we going to be left with? We get rid of this. We're going to be left with T1 over T. And then this is going to be in the numerator, the denominator. So this is going to be that. Since this is in the denominator, it moves up to there. Okay. Now we're looking even better. So now we're starting to isolate t. Now what can we do? We can divide this side by this term, which is going to make it identical to this. So what we can do, get rid of that equals, get rid of this. Reciprocal, that is just going to become a plus 1 for us. It's going to equal P pressure over the known pressure. Okay. We're really moving now. So what can we do with this right here? There's nothing much that we can really do, but there is one simplification I would like to make. Since we have an ideal gas, we know that the change in enthalpy is going to be equal to the change in internal energy plus R times the change in temperature. Okay. Now, if we're looking at this, we already know what du was from before. I believe that it was it CV? Yes, CV dt. The specific heat at a specific volume multiplied by dt. Okay, so we know that that's a dt. Now, what do we know about this? We know that enthalpy is also very dependent upon heat. Now, what is this going to be equal to? This is going to be equal to the specific heat at a specific pressure with multiplied by the derivative of the temperature. So now we have a bunch of dt's. Get rid of these, and what we're left with is this relationship. Cp is going to be equal to Cv plus R. Now what do we have here? We have Cv over R plus 1. Couldn't this be rewritten as Cv plus R over R? Meaning that we can simplify this just a little bit, so that this is going to become C, the specific heat at specific pressure, over R. Okay. And we are most definitely getting somewhere. We're about to get to the fun part, I promise. So what we have now is we have this right here. What can we do to simplify this? What we can do is we can raise both of these to multiply each, raise each to the reciprocal power. So if we raise this to the R over Cp, that'll get rid of all that. We raise this to the R over Cp. And we are left with T over T1 equals that. So what can we do? We can simply just multiply this by T1. Pretty good, right? Here, what I'm going to do is I'm going to write this in the bottom corner. Okay. The reason I'm writing it down here, I'm going to put a box around it, is because it's going to become very important to us. After we manipulate this for pressure, we're going to manipulate this with our pressure equation. Okay. So now we can get into the real nitty-gritty. Now we can substitute this t up there. Hello, I'm back. We have not made a mistake. So we're back at the same place we just were. So what I was trying to think of was I knew of what this was supposed to be. But what I didn't realize was that I was trying to plug this p, I was just trying to plug it in right here. So that would become a 1 plus r over cp, correct? But what I realized is that we're substituting in for this t here. So what I actually need to do is this becomes a denominator since it's in the numerator of the denominator, so this is going to become a negative. So what we can do is we can make this a p raised to the 1 minus r over cp. Specific heat at specific pressure. Okay, now what can we do with this? We'll cross out as we go. So we have this term right here. We also have this r. We also have this t1. Yes, we have that r, we have that t1. And then what do we also have? We also have this p1 value, which is in the denominator of the denominator, so this is going to be put up top as a positive value. It's r over cp. Okay. Yes, I'm actually going to uncross this out for us real quick, because we're going to need this later, as I've said. So now we're looking at this. What can we do? We have a bunch of nonsense here. What we're going to do is, like we did earlier, we have two equations. We're going to integrate them side by side. So what we're going to have, we're going to flip this over to here. So we're going to divide that value. So this is going to become positive. This is going to become negative 1. So we're going to integrate p to the r over cp minus 1. Derivative of the pressure in there is going to be equal to, now all of this here, excluding this, get that out of here, that is all constant. So what we're going to do is we're going to leave that outside of our integral. And then what I'm going to do is I'm going to simplify this. So what we're going to do is we're going to move this dz over here. We're going to evaluate it from our known altitude to the unknown altitude. Now, how do we integrate that? Just like a dx, you just evaluate x from here to there. So it would simply just be z minus z1. Simple integration, no need to write out the integral for simplicity's sake. We understand that this is how you would integrate this term right here. Okay, now how are we going to integrate this term right here? Actually going to erase this. I believe that we have everything we need. Yes, we do. Just to make some room for everything else. How are we going to integrate this? And we have an exponent. What we're going to do is we're going to add 1, which is perfect because, as you can see, we have this negative 1 right here, r over the specific heat at specific pressure minus 1. So that becomes a plus 1, and with any fractional exponent, we are going to multiply by the reciprocal. It's going to become the specific heat at specific pressure over r multiplied by p raised to the r over cp still. We're going to subtract, the bounds of integration as well. We have the known pressure that we talked about, the known pocket of air, known altitude, known pressure, known temperature, known volume, everything like that. We're going to be integrating to the unknown p. So when we do that, what we're going to end up with is what I've told you, minus p1, the known pressure, r to the cp as well, is going to equal. Now to save space, I'm actually going to just flip this now. So what we're going to have is p1 times r over cp, parentheses. We're going to have, another simplification I can make is we can have this, and since this is now on this side, we can have this right here, and then we can do 1 minus for our sake, right? We're going to make that 1 minus because everything in here is going to be multiplied by that. We have that term, pretend that's right here out front. It's the p1r to the cp, which that is as well. So if that's out front, we have this factoring into everything, so it's just multiplying. Anyway, let's just move on. We have minus the molecular weight of our gas multiplied by g multiplied by, actually nothing, over RT1. Now, a quick thing that I want to do that I just realized I forgot. This R right here, we remove this R. I'll just erase it. What we're going to do is we're going to divide by the specific heat at a specific pressure. So we're going to put that value down there, that variable down there. And what we're going to do is we're going to multiply that by Z minus Z1. Okay, now what's left to do? We raise everything to the reciprocal of this. So we're going to multiply by the specific heat at specific pressure over R. So what we're going to be left with, we'll put down here, the pressure is going to equal, and this is going to cancel, and it's going to be put right over here. Or is it CP over R? Yeah, it's CP over R. I hope you can see that far over there. There's a little bit of shadows in there. Okay, so we have P is going to be equal to P1 multiplied by 1 minus the molecular weight of our gas multiplied by the gravitational constant G over the specific heat with at a specific pressure multiplied by the T1, the temperature at our known altitude, multiplied by Z minus Z1, our altitude minus our known altitude. All of that raised to the specific heat at specific pressure all over R. Now this is going to be our equation. So how are we going to get our other equation? Well, simply put, all we're going to do, I don't need this up here anymore, is we're just going to take this and plug it right into there. So let's just get right into it. Okay. So what we're going to have is we are going to have T is going to be equal to T1. Now there's going to be a little bit of cancellations. We have P, we have P1. So we're going to have, when sitting in for P, we have this P1 right here, we have this P1 down here. Our P1s are going to cancel. So we're going to be left with is T1 multiplied by 1 minus molecular weight of our gas, of our fluid, multiplied by the gravitational constant G, all over, believe that stays. Yes, that does stay. Indeed it does. Whew. 1 minus that, all over our specific heat at our specific pressure, multiplied by T1, and then we have our Z minus Z1, which stays as well, our altitude minus our known altitude. And if you look at this, look at that. These two are going to cancel. R divided by R, the constant or specific heat at specific pressure, those are going to cancel out, so we have no exponent, and this is going to be our final expression for temperature. Well, I thank you very much for joining me today, and yeah, what we did today was we derived expressions for pressure and temperature. I'll get rid of this one. For pressure and temperature as functions of our variable Z. So if you look at these, that is the only unknown that we have in each. This is known, well obviously one is known, this is known, all of it is known except for Z. So we successfully did that, we derived these expressions, and I thank you for watching. Have a good day.